Hi, welcome to our poster presentation. We're from the University of Hartford and our research is based on the standardization of 3D printed microfluidic chips with application for protein biomarker detection. Presently, most protein biomarker testing for clinical diagnostics takes place in dedicated centralized laboratories using large automated analyzers. This requires samples to be transported to a testing site, increasing wait times and administrative and medical costs. Development of point-of-care or POC devices similar to that of a glucose meter would revolutionize healthcare. In order for the device to be used in a POC setting, the device must be small, have a disposable sensor chip, require minimal amounts of sample and reagents, be technically simple to use, and require minimal cost.
We constructed a screen-printed 3-electrode electrochemical chip that consisted of a silver-silver chloride pseudo-reference electrode, a carbon counter-electrode, and 8 working electrodes. The silver-silver chloride electrode was prepared through a deposition of bleach on the screen-printed silver ink. Screen-printed arrays using carbon and silver inks present many advantages such as providing a commercially scalable method to print several hundreds of high-resolution electrodes. To house these sensors chips, we constructed a novel 3D printed microfluidic device using Fusion 360 design software and a Formlabs 2 3D printer. Our novel 3D printed devices are adhered to the screen printed electrodes using commercially available double-sided tape. A Formlabs 2 3D printer was used to produce the devices, providing efficacy and dependability of the combined microfluidic electrode system. The platform was specifically designed for eventual protein detection. This is a schematic representation for how the proteins will be detected. However, before we could use the sensor chip and device for protein detection, we characterize the sensor platform.
Using an open circuit potential analysis, we investigated the deposition of bleach on the electrode surface in terms of concentration and time in forming our reference electrode. The ability for our pseudo-reference to hold potential over 30 minutes versus a commercially available silver-silver chloride reference is shown. A deposition of using a concentration of 86.3 milligrams per milliliters of bleach was optimal and used to continue out our characterization. Below, an image of cyclic voltammograms of all 8 working electrodes are displayed, of 10 millimolar ferrocyanide and 100 millimolar potassium chloride as current versus time is measured. This displays the reproducibility of our array.
Using this novel disposable sensor chip and 3D microfluidic platform, we aim to detect clinically relevant breast cancer biomarker human epidermal growth factor receptor 2, or HER2. In order to detect HER2 on the sensor surface, we will tether antibodies specific to HER2 on the sensor surface. Refer to the poster diagram. HER2 will attach and be followed by a secondary antibody with an electroactive enzyme label for signal generation. We aim to reach clinically relevant detection limits for HER2 below 7 nanograms per milliliter. This will provide an excellent, minimally invasive finger prick type alternative to current methods of detection of HER2. Thank you very much for your time.